now I've skipped over training a couple of times. Training, this is where a lot of the heavyweight math comes. And so the real like gurus and really like famous people, they figure out good ways to train models. And the way you train a model is you start on the left with an input. So let's say your input is X, an array 1, 2, 3, and paired with X is a label. And label is actually the term that's often used, which is the correct expected output from that input. In this case, that's Y equals 6. And I chose X and Y and input and label for a reason, because those are actually typically the words that people would use to describe it. If you describe something as X and Y, most people would know. If you describe it as an input and a label, most people would know. X as an input and then label, people would know, what that is. So you gather up a huge batch of these. Typically to train, you're talking about thousands to tens of thousands to hundreds of thousands. For the GPT, they were actually training with billions of samples. Each one of those samples is actually that simple. It has a pair, an input and an output label. It has a pair of those things. And when you train, the way it's actually described is you do a forward pass. All that is an inference. Model isn't doing it's not learning, it's not adapting, it's not doing anything. It just runs an inference. And at the end of that inference, let's just say in this one training sample, it gives you the output that Y equals 4.2. So what you want to do is create a feedback loop. And there's some heavyweight math behind this feedback loop. But in effect, you want to tell the model, hey guys, the answer was 6. You got 4.2. And a bit like a mad scientist, like in those movies, the mad scientist, they have that board of all this electronics behind them and all these knobs, and the mad scientist runs the knobs and they start turning all the knobs, right? That is training a model, okay? Now, what you actually do is something called back propagation. And this is sort of the complicated math, but the intuition is actually pretty straightforward. You can model this as an incredibly large math function. And if you remember some of the basic principles of differential calculus, some of the basic ideas are like, what do you do with a derivative? Or what do you do with a derivative of a derivative? It's pretty good at telling you in a particular area how to minimize or maximize the value of that function, right? That's largely what derivatives do. You remember like all those little graphs and pictures, hey, the derivative will kind of tell you where the curve flattens out or where the top of it is. It'll tell you where the bottom, of a value is. That's largely what you do with calculus. So, and this is pretty clever. They define a loss, and they say, all right, let's basically apply calculus. What we want to do is we want to optimize the loss. So the loss, in effect, is we were expecting 6 and we got 4.2. Now, computationally, it could theoretically be laid out like, hey, here's the billions of different parameters in this enormous equation. In theory, somebody could actually write it out on like the longest whiteboard in the history, of the world. But practically speaking, it's impossible to compute. So what they do is they say, well, we can't compute the exact answer to figure out how to optimize this to get every knob tuned the right way. But what we can do, if we're clever here, is we can use the gradients, the derivatives of this function to at least point us in the direction of where it looks like we're going to find a local minima in the loss. Now, it's not perfect. It won't tell us exactly all 175 billion parameters, how to tune every single one to get to the lowest possible loss, but it can kind of point us in the right direction. it can kind of nudge the model a little bit. So what it actually does then, and this is actually literally how a training loop gets written. You do that forward pass. You then actually run this backward pass, and you have an optimizer, and the optimizer runs this sort of back propagation, this calculus stuff. It's what GPUs do super, super fast. It computes all the gradients of all these different nodes. And then what it actually does is it says, tune this knob, yeah, a little bit to the right. Yeah, tune that one a little bit to the left. That one, yeah, move that. Yeah, this one, yeah, that one's good. And it's literally, you're just shaking the knobs like a mad scientist. You're turning the knobs in the ways that you think is probably in the direction of lowering your loss. But you don't know exactly. And there's always a risk that you could overshoot. You could wind up turning all the knobs in such a way because you're overreacting, so to speak, to the fact that just one or two samples were way off. So there's something called a learning rate. You've seen that in our product, the learning rate. The learning rate is basically how much you shake each little knob, how much you adjust each parameter at every training step. The higher the learning rate, the more adjustment you're going to make. That's like turning a knob from 2 to 10. If the learning rate is really, really small, 2 to 2.1. If your learning rate is too low, it might take forever to train the model. If your learning rate is too high, you can actually fry out the model, and then you actually get really bad results. So in the training loops, you have a warm-up cycle. And this is sort of well-defined. Again, in research papers, they'll actually say we use the warm-up steps, that you start with a very, very low learning rate while the model's kind of warming up. You don't want it to overreact to any one sample. So you warm up the model, which means you're raising your learning rate, as you go. You hold your learning rate at a certain level. And then once you've seen thousands to millions of samples, you start incrementally lowering the learning rate because you figure at that point, the models have probably, it's been adjusting all the parameters. The knobs are getting tuned in the right way. And again, you don't want it to overreact. So your learning rate tails off as you go. But a big part, like operationally, of what leading edge AI researchers and stuff talk about are just these sorts of things. What optimizer did you use? Oh, I used this, version of, differential calculus to compute the gradients. And I would add this to it because it makes it a little bit more resistant, to change. What learning rate did you use? Oh, well, at the learning rate after this many samples, I adjusted it down or I adjusted it up. Or when I see this thing happening, then I do this. It's basically like cooking the model. They're called hyperparameters. But those hyperparameters are really, you could think about what a chef might do, looking at a cake that they have in the oven. Turn the temperature down, turn the temperature up, take it out for a minute, blow on it, do certain things at various steps. That's really what people are doing when they're training. And it's rarely in abstract, incredibly obtuse things. It's usually pretty simple things of how much do you want to turn the knobs of the parameters at every training step. So what's actually happening when you run a training, you have millions and millions of samples. Sample number 1, you run the forward pass. You do this optimization, your mad scientist starts turning all the knobs. Sample number 2, run that through, still off. Mad scientist turns the knobs. Number 3, forward pass, adjust the knobs. And through almost brute force, but through a relatively smart calculus algorithm, you get closer and closer and closer and closer. The reason transformers have been so successful is they train really well. And again, today, people might write all kinds of papers on like, well, transformers have all this magic to their architecture. It's really just, it works. No one really understands what's in the details of it. But what it's been shown is that you can train it pretty well. It's responsive to training samples, and it learns the patterns in them really, really well. And then it scales up. So from a pure practical point of view, they can stack these layers of transformers, and they've shown that they can be trained really, really well. Years ago, people would have said there's no way you could train a 175 billion parameter model. It just won't work. Just too big, it's too complicated, there'll be too much noise. Part of the power of the transformer architecture is that it enables it to scale in that way. So when you're doing this training, the parameters are being adjusted. The parameters or weights in the model are changing while you're training. Once you're done training, you stop adjusting the parameters, and then you just run inferences. And in running inferences, the parameters don't change at all. Now, from what I just described, you can look at training a model and say, man, yeah, you hear about all this labeling stuff. I mean, gosh, it sounds pretty hard. Like you need millions of samples paired, an input and then a correctly labeled output. Well, there are two main paradigms of training. One is called supervised training. Supervised training is exactly what you would picture. It's you go out, you find samples, you label every single one of those samples. Historically, that's been most of machine learning. Two big challenges. Obviously, the cost and complexity of it, but lots of generalization challenges. And I was running these kinds of experiments, like, I won't go into all the details of it, but it doesn't generalize well. Why don't we have self-driving cars today at scale? It isn't because people don't have a basic idea of how to do it. It's there's a lot of exceptions, and it becomes incredibly resource and time intensive to keep finding more and more samples. Let's find a sample where the sunlight is coming in at this angle and a stop sign looks like this. And it's just the sheer number of samples that you need to generalize to a 5 nines kind of condition where the model can correctly visually process things. It's very, very hard, very hard. So what's always happened, for many, many years are unsupervised strategies. And today people will also talk a lot about self-supervised. Here the idea is, can you use naturally recurring patterns in the data to start training models without doing all that labeling work? And when you look at the breakthroughs in NLP, most of them have come from unsupervised or this so-called self-supervised learning. Now you might say, well, how the heck does that work? That kind of seems like contradictory. Like how do you train something with a correct label without, labeling it? And I'm going to give 3 examples on the right. I'm going to spend a few minutes walking through it because they're very, very intuitive. And once it kind of clicks, you're like, oh, this makes perfect sense. It's actually brilliant in its simplicity. Around 10 years ago, Google published a famous paper called Word to Vec. And the insight behind it was so simple, like it was sort of the brilliance of it. Basically said, hey, look at any sentence. You can take a very simple sentence. The fireworks lit up the night sky. Well, the words aren't randomly associated with each other. In fact, fireworks, lit, night sky actually have a lot of correlation with each other. So what if we just took a book, we broke it down into a whole bunch of different sentences? That's pretty easy to do. We can find lots of that. And then what we're going to do, our input and our output, they called the target and the context. They basically said, all right, we'll go through a sentence, we'll randomly pick a word out of it, and then the words that are around it, we'll call the context. And then our training sample, the input is fireworks, the output is lit up the night sky. And what the model will then learn, it'll start to learn over time the correlations between different words. So if there are enough samples that show that fireworks and night sky happen over and over and over and over and over again, it'll start to correlate fireworks with night, with sky. And in other sentences, it'll probably start attaching fireworks with 4th of July, holidays, Chinese New Year, because in those sentences, that target word of fireworks is oftentimes linked to contexts that have those other surrounding words in it. And so they were able to do some really large scale training to figure out word level embeddings, the correlation between different words and the meaning of different words, without having one single labeled sentence. Now, the next evolution in that was BERT, which uses something called masked language modeling. A very simple idea, but it basically said, aha, if we're clever here, every sentence basically can be used of we will randomly go through sentences, we will apply a mask to that to a keyword, and then we will create training samples with the input being the sentence with a mask, and then the output being the masked word. And again, what it will start to learn are the statistical correlations and the meanings between things so that it'll start to associate. Well, it could be president that announced a series of new laws. And again, maybe 68% of the time it's president, but sometimes it might be Congress, might be prime minister, might be, legislator. There would be other things that through billions and billions of words and sentences, it will start to learn those statistical patterns. And it will do that without any labeling. It's naturally finding the patterns in the language. Now, the most clever one, because it's had the most commercial success, was GPT. They said, we got an even easier test. Predict next token. The beauty of this is you can take any sentence, baseball flew through the sky and the fans began to cheer. You can break it into two. You can have as an input, the baseball flew through the, and then your output is the target completion, sky, and the fans began to cheer. Now, again, if you go through any large corpus and you start breaking up text in this way, you might say, well, yeah, if you do 100 examples, what the heck is it going to learn? The beauty of unsupervised learning is that you can do it at massive scale. So GPT has been trained each time on 300 billion tokens. Google and several of its models and Facebook have trained on trillions of tokens. So if you basically do this type of approach with massive, massive volume, it's almost like beating something over the head. And then if you have a massive model that's been optimized really well to learn, it's amazing what GPT has learned through this. And a lot of people didn't think it would ever get as sophisticated as it is, but the core of the GPT-3 model, and there is a nuance to it that we'll get into in the future, but the core of their model is this simple: predict the next word. And again, there's an intuition around it of if, like games you'd play as a kid, like we'd go around in a circle and you'd have to say a word and then the next person would have to complete the sentence. There is a certain logic to it of that's how you learn to communicate, is given a certain string of words that precede it, kind of what's the word that comes next and comes next and comes next, and keep adjusting that context of it. To a great degree, that's how you form sensible, language. So a big part of AI Bloks is we have the capability at scale to take an abundant source of language that's domain specific, document specific, enterprise specific, functionally specific, that actually is really a nightmare to start aggregating and organizing and cleaning and packaging and breaking up into small pieces. We can automate that entire life cycle to go from industry domain documents into model ready data sets. And again, you might say, but no, that doesn't seem right, Darren. It doesn't seem right. Like, how can you do that? Because you have to label it, right? What are they going to do with that? You got to label it. This is the power of these unsupervised and self-supervised strategies. There are a number of other strategies like this that we deploy in all those 16 different types of data sets, but they're being packaged for a domain-specific use to do fine-tuning training, embracing the kind of strategies that have been used on these large-scale language models. Now, there are some tasks that are pretty hard to do without labeled data. Text classification being a great example of that. But the state of the art is really evolving, and people are figuring out really creative ways to kind of bootstrap of how do you take a pre-trained BERT model that has a pretty good general understanding of language. How can you fine tune that on a domain in an unsupervised way? And then with a smaller labeled data set, start teaching it to classify in some industry specific way. And there's a whole kind of emerging area that's going on around this. One of the things that we embraced in our product is the sentence transformers. We have a fantastic unsupervised training recipe that can start with a pre-trained BERT. We use some out-of-the-box, state-of-the-art, industry data sets, combined then with your domain, your industry, and out of the box, we can do a full end-to-end training loop to help somebody fine-tune a model for their domain without any labeling. So it truly is that simple and that straightforward to do.